my desktop. Okay. In the name of God, and hello to all dear students. In this session, we will continue the concept of topological space, and in this definition we see the definition of a subspace. Let X and tau be a topological space and Y be a subset of X. We define the restriction of tau to Y by this family of sets, intersection of Y and U for all U in tau. It is clear that this set is a topology on Y, and this topology is called the topology inherited from X. Okay? So we have one original topology on X, then we construct a topology on Y because all of these sets are subsets of Y. Okay? So tau Y is the intersection of all open sets of X by Y. Tau Y by this notation or this notation is this set. The intersection of all elements of tau by Y. And it is clear that tau Y is a topology. Let me write this for you. For example, let's X and tau be a topological space. Okay? And Y be a subset of X. If tau Y equal to this set, the set of all these intersections such that U belong to tau, then tau Y is a topology on Y. It is clear that all of this is a subset of Y. Okay? Tau Y is a subset of P of Y. And we have these properties that, for example, empty set equal to empty set intersect by y. Okay, so that empty set belong to y, because we know that empty set belong to tau. Okay, empty set is an element of tau, so we can choose this u equal to empty set. And also y equal to intersection of x and y, and this is belong to tau y, because we know that x is an element of tau, and in this we know that empty set is an element of tau. Okay, and two, if we consider a family such as this, for example, okay, let me write two elements. Okay, it is not important. I b into y. Then for each alpha in I, there exists O alpha in tau such that U alpha equal to O alpha intersect by Y. Okay, because all element of tau Y but must have this form. Okay, for one open subset of 2, so that the union of U alpha, for example, equal to the union of these sets. Okay, and this is equal to the union of O alpha intersect by Y, and this is belong to tau Y, because this is an open set. This is belong to tau. Okay, because this union belong to tau. Alpha belong to I. This union is an element of tau, so that this intersection must belong to tau Y. And finally, three, if for example u1 and u2 belong to 2y, then there exists O1 and O2, for example, in 2 such that U1 equal to O1 intersect by Y and U2 equal to O2 intersect by Y. So intersection of U1 and U2 equal to intersection by these two. Okay, this intersect by this, and this is equal to O1 intersect by O2, then intersect by Y, and this is an element of 2Y because this is an element of 2. This is an element of the original topology in 2. Okay, so that if you consider this subset of Y, this consists a topology on Y. Please note that 2 is a subset of P of X and 2Y is a subset of P of Y. Okay, dear students, do you have my voice? Welcome Mr. Ali Shahmani, Muhammad Al-Khafaji and other students. Okay, and we showed this in this diagram. If for example this is our original set X with topology such as this, we must consider intersection of any element of 2 by Y. This intersection, these are subsets of Y, and these sets, this family of sets consists a topology on Y, because we have these three properties that I proved this for you. Okay, and we have this trivial example. If we consider 2 equal to discrete topology P of X, then 2Y equal to P of Y, discrete topology on Y, so that the inherited topology of X on Y equal to discrete topology. For the proof of this equality, I say that we always have 2Y is a subset of P of Y. Conversely, if R be a subset of Y, or A belong to this set P of Y, or A be a subset of Y, then we see that A equal to the intersection of A and Y. And we know that this A is a subset of X. A is a subset of X, and this is equal to 2, so that A is an element of 2 of Y. And also we can take this example if we consider X equal to this set 1, 2, 3, 4, 5, and Y equal to this subset of X 1, 3, and 5, and we consider 2 equal to this, then we see that The singleton 3 is an element of 2y because we can write 3 equal to this set equal intersected by y. This set intersection by y equal to 1.3. Since this is an element of 2, we see that this is an element of 2, so that this intersection by y must belong to 2y. And this is an element of 2y because we can write this set equal to 1, 2, 3 intersect by y, and 1, 2, 3 is an element of 2, so that this is an element of 2y. And other example. Okay. We see this proposition in the previous session. Okay, we see this proposition in the previous session. A topological space is Hausdorff if and only if every net in X has at most one limit. And also we have the definition of coordinate project. Let this family be a family of topological spaces, and X and 2 be a topological the topological product the functions pi from X to Xi defined by pi of any element in product space equal to i's coordinate. Okay, we can it is better that we say X be the product space. Okay, because we define product topology in the following. This is be a family of topological space, and X or this I belong to I, B its product set. Okay, not topological product, topological set. Please note that as a remark, if Xi, for example, be a family of sets, okay, then the product of this family is the following set. We denoted this by this notation, but this is equal to the set of all f from I to the union of these families, okay? Such that for any I in I, f of I belong to xi, okay? F of I belong to xi. Please note that if I or index set I equal to an empty set such as this, then this product space okay equal to and it is very easy to understand because in this case f belong to this product if and only if for any I in this set if I belong to xi, okay? So that we can consider f by this n tube f1 up to the fn belong to x1 xn because we want that f1 belong to x1, f2 belong to x2 and fn belong to xn, so that this n tube must be belong to this n product space, okay? So that we can consider any element of this product space as this n tube. And also if I equal to 1, 2 up to the infinity, by the similar method we see that this product space I belong to I or I belong to n natural numbers equal to x1 multiplied by x2 up to the n. For this reason, in our book, any element of product space denoted by this notation. But please note that if I be an uncountable set, the element of product sets is not necessary by this form. Okay, it's not necessary by this form. So in the general case, you can write this definition. If xi is a family of sets, then the coordinate projection, okay, for each I in the set I, the coordinate projection on xi is this function pi from the product space, okay, to xi by this function rules for each f in this product space. Pi of f equal to f of I, only f of I, and we know that f of I is an element of xi. This is more carefully for define coordinate projection, okay. And it is very clear that in the case that I equal to this finite set, for any I in y up to the n, pi of this element in product space equal to xi, and also in the case I equal to natural numbers, pi of any sequence equal to xi, okay. These two are two special cases of coordinate project. Now we can define product topology on X. So at the first we have a family of sets. From this we define product space of this family, product of this set. Okay, we can consider this as an X. Now if each of these sets have one topology such as this, we want to define a topology on X, and this is product topology. Okay, product topology. Let this be a family of topological space, and let X be its product space. Can we define these as sets? Depending on whether or not I is finite set, we can have two different topologies on X. If I is finite, then we use the box topology equal to this, and if it's an infinite set, then box topology would have too many elements to retain its desirable properties. Tikhonov topology. Instead, in this case, okay, we define to be the correct topology. Make the coordinate projection pi be continuous. The product topology is generated from this base as a base of our topology. Okay, I think I write this for you. Okay, this is the definition of product topology that I write this for you. Okay, this is the definition of product topology. If I is finite, product topology is equal to box topology. The product of UI, where UI are into I or are open subsets, or equivalently this product space. And if I is infinite, the correct topology on X such that for each I, this projection be continuous, so that for each I, pi must be continuous, and so for each okay, for any open subset of Xi, the inverse image of UI must be open in X, so that must be belong to the topology of X. Please note that we see this important proposition. that a function such as f from x to y is continued on whole of x if and only if for any open subset of y the inverse image of this open set be open set in x, and also for closed set. Now we have pi coordinate projections, okay? For any I, pi must be continuous so that for any open subset of this y, its inverse image must be open or must be belong to orthopology. So that orthopology is very clear for any I. Since pi must be continuous, the inverse image of any open set must be open in x. For any ui in 2i, this inverse image must be belong to 2. Please note that. The inverse image of ui under pi equal to this product that only ui equal to vi, and for any j non-equal I, vj equal to xi. It is very trivial because let me write this for you. If ui be a subset of xi, for example, then the inverse image of ui equal to, because we know that pi is a set of x to xi, the set of all f in x, for example, such that pi of f belong to ui, and this is equal to the set of all f such that f of I belong to ui, because we know that pi of f equal to fi, f of I. This is the definition of coordinate projection, okay? Coordinate projection, pi of f equal to f of I. So we have only control on f of I, and for each j non-equal I we don't have any restriction, okay? So that this is equal to this product. For example, we can write this product I belong to I. For example, di such that di equal to ui and dj equal to xj for all j non-equal I. And in the finite case or countable case, we can write this very easy. For example, if we consider I equal to for example P1 minus 1 of ui equal to u1 multiplied by x2 up to xn. P2 minus 1, let me write this u1 for example. u1, okay, and this is equal to x1 multiplied by u2 multiplied by x3 multiplied by xn, okay, and finally Pn minus 1 un equal to x1 multiplied by xn minus 1 multiplied by un, okay. Only we see u1 in the first coordinate, u2 in the second coordinate, and un in the nth coordinate, and other coordinate equal to whole of x, j for example, okay. Dear students, do you have my voice? Mr. Sajjad, Hassan, Muhammad. Okay. It is clear or difficult? Dear students, it is clear? It is easy or difficult? Do you understand? Let me write this for you. هل تفهم البراهين؟ Okay. Very good. So that in product topology, all of these projections must be continuous, so that we have this as our base. The topology that generated by this base is product topology. Okay. So if we consider a family of topological space and XP its product set, we define tau as a topology on X by the following method. The Caresses topology on X such that for any I, Pi from X to Xi is continuous. This is equal to the topology generated by the following base, this base, okay? And the topology generated by this subbase. This is the subbase for product topology and this is the base for product topology. Okay. It is not that if we consider this set as of subbase, let me write in countable case. In countable case, if we intersect, for example, this inverse image by this inverse image, okay, this is equal to x1, x2 and ui, then up to there. Intersection by x1, x2 uj xj plus 1 multiplied by xn, and these two equal to x1, x2, for example xi minus 1, then ui, then xi plus 1, then xj minus 1, then uj, and xj plus 1, finally xn. So we have these two position, ui and uj. Other one are whole of xj or x car, x1, x2 up to there. Okay. The intersection of these two are this. Now I say that if we have this subbase, any finite intersection of this set must be open and must be in all base. Any finite intersection of this form sets consists this beta as our base for our topology. And this is important that we define the product topology and we introduce its base and its subbase. Example, consider R real numbers with the Euclidean topology. We can take n copies of R and use the box topology on get R to the power of n. Since this is a finite product, the box and product topology are the same. In Rm, this product is an example of an open set. This must be product. Okay? Not very good. This multiplied by this multiplied, because all of these are open, so that this product is open in product topology or in box topology. And in any topological space for any subset of X, an open cover such as O of S is a collection of open sets that contain S. Is a collection of open sets that contain n S. By this definition, S must be a subset of the union of this family. Then we say that this is an open cover. Please note that. If, for example, we consider this that this is our S, for example, and this is our set X. If we consider UI, for example, into X and 2 is a topological space, okay? UI is an open cover for S if and only if we have two properties: for each UI be open, and two, S be a subset of the union of UI. Okay? So that if you consider some element open sets. Okay, open sets. These are open sets or open subset of 2. If the union of these sets contains S, we say that this family is a cover for S, is a cover, because these sets, the union of these sets cover whole of S. Okay, S be a subset of the union of this family, and if X and 2 be a topological space and S be a subset of X, S is called compact if every open cover have a finite subcover. And the definition of finite subcover is very easy. Any finite family of this open cover that, let me know, such as for example U1 UN, that cover S, okay, is called an open subcover, open finite subcover. Subcover, okay. A finite element of this element cover is. Now if any open cover have a finite subcover, we say that S is compact. F is compact. Okay, we have a very important proposition. If this is a compact space and Y be a topological space and F be a continuous function, then F of X is compact too. The image of any compact set under any continuous function is compact too. Is compact too. I write definition of compact subset. S is compact if and only for any open cover for S there exists finite number of this cover, such as A alpha 1, A alpha n, such that this alpha n, okay, alpha 1 up to the alpha n, A alpha n. Such that S is a subset of this finite union. Or equivalently, for any family of tau that we have this relation, there exists a finite number of this index sets such as alpha 1 up to the alpha n, such that S is a subset of this union. Now we have this proposition. If f from x to y is continuous and S be a compact subset of x, then f of s is compact in y too. Because if we consider an open cover for f of s be a subset of this union, then we can take the inverse image under f. The inverse image of this is a subset of inverse image of this set. And so this is S. Let me correct this. This is S. Okay. So that S is a subset of, because we know that this inverse image equal to this union. But for any alpha, the inverse image of A alpha is open, because A alpha is open and F is continuous. So that all of these are open set. So that this is an open cover for S, but S is compact. S is compact. So that a finite number of this must be covered S. There exists a finite index such as alpha 1 up to the alpha n, such that S is a subset of this union. So that we can take f of S is a subset of f of this union, and f of this union equal to union of f, and this equal to A alpha 1. So that for any open cover for f of s, we find a finite open cover for this, so that f of s is compact. Okay. I proved a generalization of this for any compact subset of x, f of s is compact. So that, dear students, it is enough for this session, because we must begin the second class operator theory. We will continue in the next session, inshallah. Do you have any question? Do you have any questions? Okay, thank you. Goodbye for now. Goodbye, dear students.